So these are lectures that Grothendieck gave in 1973. He had announced that he was leaving the organized practice of mathematics. He was raising money for Survivre et Vivre, his ecological group. And so he gave a series of lectures, several lectures over several years. This picture is actually in Montreal in 1971, but it's close to this time. In Buffalo, he gave 3 series of lectures. He gave a series on topos, he gave a series on algebraic geometry, and one on algebraic groups. I have not listened to the other 2 series closely enough to figure out exactly what was scheduled. He did say at one point that the only one he was thinking about was the series on topos. The others were routine. And even the series on topos clearly begins as just an introduction to the subject. He's simply recounting what's in SGA. SGA4 had just gone to press earlier that year, after years of editing. And he clearly began simply recounting what's in SGA4. But it was scheduled for 10 hours. We'll come to how we know that. The introductory lectures then ran 16 hours. And then there are 17 more hours of a small group on tape. We know the tapes are not quite complete. It's not perfectly clear to me how incomplete, but I think substantially complete. Yeah, okay. So here's what he has to say. As I say, when I started on categories around 55, now you might think he didn't start in 55. You might have thought that when he wrote Résumé des résultats essentiels dans la théorie des produits tensoriels topologiques et des espaces nucléaires, when he writes these things, you might think he's already involved with categories in 1952, 1953. And indeed, he's giving functorial universal descriptions of certain vector spaces. He wants to characterize, well, he was given this problem to explain some theorems in functional analysis, and he decides there's this key property that really the key to those theorems is to understand tensor products in vector spaces. And so he's going to do this by categorical means. But in 1973, he does not call this category theory. He clearly not. He's saying he began in 55. This is not because he's uncertain about the dates. This is because of what happened in 1955. In 1955, he wrote what's called his Kansas paper. Also, he substantially wrote what's called Tohoku, although that appeared in 1958. In the 1955 Kansas paper, he's approaching cohomology. As I think probably everybody here knows, his early work on functional analysis, he was assigned this as a dissertation topic, but then what he's done in 54, 55, he takes up the Weil conjectures under Serre's influence, wants to find a cohomology theory. It seems to me pretty clear that Weil did not really believe there could be a cohomology theory that would prove his conjectures. He thought it was a great way to think about the conjectures, but he didn't really believe you could do them that way. Whereas Serre did. Serre thought you could find such a cohomology theory, and he convinces Grothendieck of this. But clearly, for reasons I won't go into here, it wasn't going to be much like existing cohomology theories. You were going to have to somehow find what was the key, what was the core of cohomology, and get that to work. So Grothendieck is trying to envisage cohomology. And in the 55 Kansas report, he wants to do this, including non-commutative cohomology, cohomology with non-commutative coefficient groups. He's going to do it by interpreting groups and torsors. Well, we'll talk a little bit about that in a minute. Tors is another name for principal fiber bundles. He wants to interpret these in categories of sheaves of sets. Over every topological space has a category of sheaves of sets. He thinks he wants to look at that. And here he is clear, a sheaf is a local homeomorphism. Already we have a problem with language. Grothendieck speaks a very colloquial English. He has, I think to most American ears, a German accent, which is not that surprising because even if he was speaking French during the years he learned English, he was probably learning it from German speakers. And he seems to have learned it with a German accent. But he speaks a very colloquial English. And he says étal space over and over again. There are two French words, étaler and étal, and Grothendieck has absorbed the English speaker's habit of pronouncing them alike. He just says étal for both. Now, he means, throughout these lectures, he means étaler. He never explicitly talks about 𝐂𝐨𝐥𝐢𝐧 étal here. I haven't listened to enough. I haven't heard him saying it in the algebraic geometry lectures either, but I haven't listened to them exhaustively. I'm going to write with two accents, and I'm going to say étal space, because he always pronounces it étal space. But the other word, the word more properly, étal, doesn't occur in these lectures anyway. So a sheaf is an étal space, a sheaf of sets. So for example, you have a circle, an étal space. An étal space is a space stacked smoothly above it, so you might have this spiral stacked above it. Any little bit of this is just stacked one-to-one over a little bit of the circle, is the idea. Or here, again, any little bit of this is a double cover, and any little bit of it is stacked one-to-one over a little bit of the circle. So these are étal spaces. Now, certainly much more complicated things can happen, but again, I don't know the background of everybody here. The people I know here don't, but anyway, I don't know the background of everybody here. You can see that this thing is sort of unwinding the circle. Okay, that's great. You're saying locally it's just like a line, but it has this periodicity. So this is, I hope it's plausible that this is a good way of unfolding a space to get easier access to it. And it's a standard method. It was a standard method in topology, well, from the time Grothendieck arrived in Paris. So in the Kansas paper, he's interested in the functorial behavior of sheaves of sets. The category of sheaves on one space, well, you have a topological space X, a topological space Y, you have a continuous map between them, and this induces a functor in the other direction, what is now the inverse image functor of F. That's the one he talks about in the Kansas paper. I have not read that paper closely enough to see if you can find some anticipation of the direct image functor. Of course, he says some of the same things that we would now say with the direct image functor. But he's very interested in the fact that if you interpret some group here, this carries it over to an interpretation of groups here. So groups in this category become groups in that category, and this happens in a very nice way, a functorial way, which if you know what that is, you know. So he's interested in that. This functorial behavior, that's his word. The paper's written in English. But he does not attempt any intrinsic characterization of categories of sheaves of sets. He just, you know, you've got a topological space X, you know what's meant by a sheaf of sets on X, and they form a category. He uses properties of those categories, but he doesn't try to describe them by any categorical properties. He just knows what they are. Now, in 1973, in the Buffalo Lectures, he says that in 1955, he did characterize various kinds of structures, monoids, groups, rings, etc., in all categories with suitable exactness properties. I made a few notes to myself about what to be sure and say about the. As a historian, you look at something like this and you have to say, well, did he really? Sometimes people, you know, they remember, you know, 18 years later, he might be projecting back ideas that worked on his earlier thinking. And you have to expect that because exactness properties are pretty abstract. And in 1955, exactness properties seemed very, the existence of products, the existence of direct sums, the existence of all direct limits, all inverse limits. I won't go into what these are because if you know them, you know them, and I'm not examining them. But in 1955, those seemed like very abstract things, and so you might think, well, did he really do this in that abstraction? But I think when you look at the evidence, you have to say, yes, he did. And the reason for that is, well, besides that you can see in the 1955 paper, he doesn't declare this as a general program, but you can see that kind of thinking going on. You can see that by 1955, naive exactness was, at least for Grothendieck, much more intuitive than the nuts and bolts of sheaves. It's really an easier way to think about it, and it was already easier for Grothendieck in 1955. So if we want to interpret a group in a category, I'm not going to worry about describing. Oh.
What is the meaning of nuts and bolts?
Oh, nuts and bolts. The mechanics, getting your hands on every little part and fitting them all together. Yeah, like the screws and the bolts and the nuts that fit onto them. Yeah. Getting your hands on everything that's going on in a sheaf category is kind of complicated. But if you say, what is a group? Well, you take an elementary textbook, elementary and abstract algebra textbook, it'll say a group is a set, and it's got a binary operator to itself. It's, but Grothendieck clearly sees, it doesn't matter that this was called a set. We know what it is to take the product of two sheaves on Y. We know what it is to take a map from that to the sheaf itself on Y. These kinds of diagrams, it's much, and then we say, well, look, there should be a unit element of the group. These kinds of diagrams are easier to think about than the detailed meaning in a given sheaf category. And you can see Grothendieck already in 1955 is good at thinking about these kinds of diagrams in a sheaf category. He can get his hands on the particulars when he needs to, but he's really good at not needing to, which is absolutely how you would do it today. So I think it's really true that in 1955 he did characterize a lot of these kinds of algebraic structures in all categories with suitable exactness. We'll be talking more about that. This is a quote from 1973. According to the type of structure we are working with, monoid, torsor, topological space. Okay, those are examples he was giving around there in the tape. We will have to assume that our category C admits certain types of direct or inverse limits and that certain axioms are satisfied on these limits. And these will be the categories on which these structures make sense in a way. I will try to make this more precise, or we will try together. And here we see more evidence that this is not a hindsight projecting these things back onto the past, because in 1973, and indeed today, there's not much use interpreting topological spaces this way. That has never worked out to any valuable purpose. He's saying it because he did think it in 1955. He's certainly not saying it because it worked out well later. It didn't work out well later, hasn't worked out well to this day. You could do it in any topos, but it hasn't been valuable. So I take this as evidence that his memory here is accurate. This is what he was thinking in 1955. A monoid is like a group, but it doesn't have inverses. A torsor, I didn't describe what a torsor is. A torsor looks like a group, but it hasn't got a selected unit element, so it's sort of a group that's invariant under being rearranged. I won't go into details on that. Again, if you know them, you know them. But, and so he really is saying that I'm going to interpret groups in any category with enough abstract properties. And basically, what does that mean? You can interpret groups in any category that has a terminal object, that is one that everything has a unique arrow to, and has products of its objects. I won't give the precise definition. And then if you got those two structures, you can interpret groups. There might not be any groups in a given category that has those structures, but you can say what it means to be a group in that category. Or again, there may, and in chief categories there are, and they're very important. He says, these were the kind of things I was fumbling over a long time ago when I started on categories around 55. So for Grothendieck, this is category theory. Using categories of topological vector spaces, that's not really category theory, it's functional analysis. Using universal properties of various objects in categories of topological vector spaces, again, not category theory, functional analysis. But interpreting new kinds of structures in a category C, especially when the category C was defined just by abstract exactness properties, not by what the things in it are made of, that's category theory. And general nonsense. He calls it general nonsense fairly often in the lectures. And this is, I'm stressing this because there's been a fair amount of discussion of whether Grothendieck would ever have called himself a category theorist. Well, he doesn't use the term category theorist, but he does describe his work as category theory fairly often in these lectures. Another quote from 1973. This general nonsense, you see, to make it a mathematical statement would be kind of awkward. In fact, Chevrolet had a seminar at the very beginning of IHES, around 58 or 59, and he spent a year trying to define algebraic structures that can be described in terms of certain types of inverse limits, certain types of direct limits, and making universal constructions, etc. It was a pretty bad mess. So I don't think I will try to make it really mathematics. I like this idea of making it really mathematics. I don't think I'm going to do it. What is important is to get the general idea and have the correct, how shall I say, thought patterns for these situations so as not to use time and energy doing involved things. Now, I will say, as the ideas developed, other people took the advice that he gave in SGA4, le lecteur est prié de donner un sens mathématique à la phrase précédente, which has to do with interpreting things. Nous conseillons au lecteur de l'expliciter. Grothendieck is not saying nobody should develop this precisely. He is saying he's not going to develop it precisely. And people have, as the ideas have become more important. I mean, you had Olivier Caramello in the same lecture series, has put a lot of work into making these things mathematics. But Grothendieck, not going to try to make this really mathematics. But he does say you should do it in SGA4. Now, as to serious general nonsense, the Tohoku paper 57, I guess it appeared in print in 58. Okay, well, I mean, he spent a while trying to get it into print. He says he had the idea in 55. It characterizes injective objects in certain categories. I won't go into what injective objects are. It's a pretty simple idea to define. Finding them is another thing. It does not interpret structures like groups in categories. That's not what he's doing in this paper. But it axiomatizes the categories. These are not concretely given categories. Of course, he talks about concretely given examples that motivate the work, but the theorem does not deal with concretely given categories. It deals with categories that are defined entirely by exactness properties. They say there's concrete examples, but it doesn't. They're axiomatized by exactness properties. Oh, I didn't put, but as I put here, he's in the Kansas paper, he handled sheaf categories by exactness, but he didn't define them that way. Here, he defines the categories of interest by exactness. He defines an AB5 category. AB5 categories are important for uses in cohomology, in topology. These are a kind of category that was already important for doing cohomology as it existed in the Cartan seminar. And it's an additive category. It's a category where you can add arrows to each other, and it satisfies some other properties. It has all finite, direct, and inverse limits. images are isomorphic to co-images, it has arbitrary direct sums, it has filtered increasing families of subjects, have stable direct limits, and there's a reason I'm rushing over these definitions, which is that if you don't already know them, you're probably not going to, they're not going to mean a lot to you, and that's okay. I will say, although someone who was there might disagree with me, that in 1958, when Grothendieck published this, it was not obvious why those would be the properties you would, it's obvious why they worked. You could see those are the properties he used in his proof. There was not any prior reason to think that those would be the properties that would work. Well, there was a kind of prior reason, which is how Grothendieck found it. These were the properties that Reinhold Baer had already used some years before to embed every group, every abelian group in an injective group, every module in an injective module. So these were categorical analogs of the properties Baer had already used to prove a much more special case of the same theorem. Grothendieck, he doesn't have to invent these properties. Well, he invents them, he generalizes them, he puts them in categorical terms, but he can more or less read them off of Baer's proof, which I think was in 1948. That's where they come from in 1948. We're going to see properties like this come back for other reasons later on, but I do want to say that in 58, people looking at this list of properties thought, well, the only reason for that list is that it works. There's no conceptual reason why that would be what would work. It's just what does work. So these properties let Grothendieck handle objects in these abstract categories pretty much the way algebraists handle modules. That's supposed to say the way. I don't know why it says the say. So it's just lifted from how Baer already handled modules. But notice that Grothendieck is not building these out of elements or sections the way mathematicians use sets. In the Kansas paper, he was sort of building sheaves out of what are called their sections, sort of the way we standardly use elements of sets. None of that is going on in the Tohoku paper. Of course, the two papers get together well. They're on the same project, but they're on slightly different aspects of it. Grothendieck can now tell you any AB5 category that meets these and one other technical condition, which Grothendieck calls technical a lot. Any category meeting these and this other technical condition has a cohomology theory, a unique canonical cohomology theory. But this paper gives no clue where those categories come from. The Kansas paper was talking about where categories sort of like this might come from, although it was published before he had this result. The categorical idea of topos, as he describes it in Buffalo 1973. This is what he wants to call people's attention to. I mean, picturing what's going on here, well, besides that he's a little disaffected from mathematics, he's announced he's not going to do any more of it. He's now in Buffalo, New York, where he knows people like him a lot. A few people like him a lot. That's why he got invited. He's going to tell them roughly what a topos is. And he's going to repeat this a lot. I'm only going to quote about 8% of the times he says this. And that will already seem like a lot. The essential properties of the category of sheaves of sets on a topological space, which I have tried to convey because he said it a lot already by this point, is that it shares essentially all exactness properties of the category of sets. He says this over and over again. Oh, sorry. He says this over and over, and then he adds, at least those expressed by direct limits with arbitrary indexing diagrams and finite inverse limits. He's going to keep saying all properties and then take some of it back. So the notion of a topos, E, should be that E shares the exactness properties of the category of sets insofar as direct limits and finite inverse limits go. Moreover, for technical reasons, one has to assume that in E, there is a small subset, not as big as the whole universe we're working in, which is generating. And he keeps calling it technical, and I'm not going to go much more into that. The yoga one finally gets to is essentially the following. The category of sheaves on a topological space is just as good, with a grain of salt, as far as exactness properties are concerned, as the category of sets. The grain of salt is that this is, oh, and I would say everything in italics here is direct quote from the tapes. The italics are quotes of the tapes. The grain of salt is that this is true for all commutation relations, exactness properties involving arbitrary direct limits, which may be infinite, and also inverse limits, provided we take only finite inverse limits. And then, we're now 8.5 hours into the series, and this is how I know it was planned to be 10. What shall we do? We're supposed to finish next time. I will speak about intrinsic properties of topoi and will not have much time for getting topoi from sites. Probably I need 2 more sessions, and it might be nice to have 1 time or 2 on relations between topoi and algebraic structures. This is also, quote, I stop without really having said anything about topoi. Uh-oh. He wants to do this other topic because he says to give a type of algebraic structure seems to be the same as to give a topos, the so-called classifying topos. So there seems to be a kind of equivalence relation between algebra and topology. And he's very interested in that at this point. Oop. So these sessions were 3 hours long. I think when he says this at hour 8.5, this is my evidence that it was originally scheduled as a 10-hour series. 1/2 session, but he says, oh, what are we going to do? We're supposed to finish next time, but I'm not going to get done. So now what does he want to do? If we take it that these sessions are 3 hours, what he wants now is 13 hours of introduction of topos, and then 3 more on relations between topoi and algebraic structures. So he's now envisaging 16 hours. As you say, the total ran to 33 hours. Okay, yeah, I have those. So again, it's a category with the exactness properties of sets so far as concerns arbitrary direct limits and finite inverse limits. And so how did he pick that those were the exactness properties he was going to use? He tells us it will turn out that arbitrary inverse limits also exist. They're always going to be there. And the arbitrary inverse limits are kind of generous. They go beyond what I said, that a topos should share the exactness properties of sets in finite inverse limits and arbitrary direct limits. So there really is a problem of why does he say arbitrary direct limits and finite inverse limits when arbitrary inverse limits also exist? The only answer I can see, I mean, I think it's the correct answer, is these are the properties used in Tohoku if you drop additivity. He's saying the Tohoku properties, those are the properties I'm going to use to define topos. And this explains a peculiar line in 𝐵𝐸𝐴, where Grothendieck, he spends some time on topos. He spends very little time on abelian categories, but he does say at one point, what is an abelian category? Well, it's a category that has essentially the properties of a topos. And if you come to this knowing the material, you think, no, it doesn't have the properties of topos. But it has the exactness properties, the same exactness properties that he used to axiomatize topos. Except it's also additive, which a topos is not. He comments over and over that infinite inverse limits don't work as nicely in a topos as they do in sets. In particular, if you have an infinite product of epimorphisms, think of this as onto maps. An infinite product of them in sets is also an epimorphism, at least if you have the axiom of choice. But in a sheaf category, very commonly not. A finite product will still be an epimorphism, but an infinite product of epimorphisms will not be an epimorphism in general in a sheaf category. So there's another reason to limit the inverse limits to the finite. Only the finite ones work nicely. But I think the original reason he did limit it was that's what he used in Tohoku. Well, eventually he gives the Giraud axioms on a topos. And he gives the site definition of a topos. And I'm not going to go into that here because he tells us in the lectures, So here's the notion of a topos, which is slightly technical. He's not against it, but well, I think it's kind of intuitive, though, he says, to take the vague notion, which intuitively makes more sense, the one where you have all direct limits and finite inverse limits. He says, I have a tendency to forget which properties 𝐵𝐸 uses. Well, here they are. A locally small category with small generating set, all finite limits, all small coproducts, disjoint and stable, stably effective equivalence relations. You know, if you're a little bit used to the subject, you don't forget those anymore. But Grothendieck tended to forget them. And if you're not very used to the subject, don't worry about absorbing these, because Grothendieck has already told you they're kind of technical. What you want to think of, I guess I should say more intuitively, arbitrary direct limits means you can take a union of any number of these things, take any set of these things. You can make a union of that whole set as one of these things. And any one of these things, you can collapse it down along any equivalence relation. But inverse limits are basically products. You cannot expect to take an infinite product of these things. Well, there's that complication. Actually, there is going to be an infinite product of them, but you don't want to look at it because it's not going to work well. So, so what you want to be thinking is, whatever I'm doing, I can take arbitrary sums of these things. I can take the coproduct over any set. I can combine infinitely many of them as long as it's a set. But products, I'm only going to take products of a finite number. Other limits, I'm only going to take those on a finite number. That's what you should be thinking, he's telling you. And I say this is already over the limit of what the lectures were scheduled to reach. So there's the categorical idea in a nutshell. But he also has a geometrical idea. He says the intuition is the following. Viewing objects of a topos as being something like étale spaces over the final object of the topos, and the induced topos over an object is just the object itself. This is the way I think one should handle the situation. What is so the objects of sheaf X, well, if X was the circle, the objects are things like the spiral going over it, or the double cover going over it. The objects are also spaces that map nicely onto this thing. What is the induced topos? Whew. The induced topos on a given object A is all the arrows to A in that topos. Again, this is not something, a lot of you will be familiar with these ideas. I'm not going to try to explain them very well to people who aren't. But what I want you to get from this is an étale space over a circle is some space. It is a space that's kind of stacked neatly over the circle. And he's saying you should think of the objects in any topos as being sort of stacked neatly over the final object, the one that everything maps to. That's the way I think we should handle the situation. One should handle the situation. He says, it's a funny situation. Because in strict terms, you see, the language which I want to push through doesn't make sense. But of course, there are a number of mathematical statements which substantiate it. Okay, what doesn't make sense here? First of all, to say that all objects are étale spaces, they're not all étale spaces. I mean, you use lots of toposes where they're not étale spaces. By the existing definition of étale space, but Grothendieck is going to urge that we should redefine that. And the objects are the induced topoi. I mean, an object in the huge category of all of these things, an object here is not the same as the huge category of all maps to that object. But he's saying you should think of them as the same, because there are a number of mathematical statements which will substantiate that. Even though it can't be quite right, but it's the way you should be thinking about these things. Okay, so this means that every object in a topos is an étale space. Every arrow in a topos makes the domain an étale space over the codomain. Because every arrow in a topos, well, if A was an object here, some object here, then A becomes the final object in the induced topos of maps to A here. So every object in a topos is final object of some other topos. And every arrow to it becomes an object in this induced topos. So he's really saying you should think of all maps in a topos as making the domain an étale space over the codomain, which clearly does not always do in the existing definition of étale space, but that's what he's saying he wants you to think of. It's a funny situation. It doesn't make sense, but there are many mathematical situations that confirm it. He intends a major generalization of étale space. His favorite example of a topos is the topos of G sets for a group G. He wants sets acted on by a group. Let our group be the integers mod 4. Okay, a nice small group to think about. What are the integers mod 4? Well, Z mod 4, if you want to think of this set of elements, it's got 0, 1, 2, and 3, and you do addition modulo 4. So 1 plus 1 is 2, 2 plus 2 is 0, because it's 4, which is 0 here. 2 plus 3, well, that's 5, but that's 1, so it's 1. So, and what does a G set look for? Well, here is a simple G set for Z mod 4. You could think of it as it's got 4 points, and the element 0 of the group acts by leaving each one where it is. To act the element 0 on this group, leave everything where it is. To act the element 1 on this group, move everything 1 step. To act 2, move everything 2 steps. 3, move everything 3 steps. To act 4 on it, move everything 4 steps, but that takes it back where it was. You might as well have moved it 0 steps. So this is well defined for integers mod 4. That's one simple G set. But another one is where you've just got 2 elements. To act 1, you move it 1. To act 2, you move it 2. So 2 already takes it back where it used to be. But the point is that 4 also takes it back where it used to be. And then you've got another one where everything leaves the point alone. So every G set is some set of orbits like this. These are the orbits. A G set is any set-sized combination of these orbits. Now, these are not étale spaces over each other. These are group actions. Over a given point, especially, look at what these stack over a fixed point. Over this fixed point, you get an orbit. Well, any set of orbits, if your G set was some bigger collection of orbits, they're all stacked over there. So each orbit is étale over every quotient of it. That's the reform he's suggesting. Now, this slogan that objects of a topos are étale spaces over the final object, I will point out that SGA4 had already explored reasons this might not work well for all cases. It might work well only for what are called petit topos. He had already explored reasons why it might be limited. Lavire has pursued this, but there is still no general definition of a petit topos. There are canonical cases, there are clear cases, the petit étale topos of a scheme, petit topological topoi, but there's no general definition of petit topos. And Grothendieck actually explored that some in an exercise in SGA4. It's a several-step exercise, and the last step is to buy a chocolate medal for the author of these exercises. Médaille en chocolat. You're supposed to buy him one for these exercises. So he evidently liked those exercises. So what I want to stress here is that it's likely that in 1973, Grothendieck did not believe this would work well for every topos. he's not concerned with whether it works well for every topos. He is concerned to say it's a good general way to think about topos. But it works very well for what are called petit étal sites. With the generalization that he's offered. Do I have a, yeah. The thing is that étal sheaves put Galois orbits over single points of a scheme. So it's like when we're having those G sets all étal over a single point, you have to notice that what's étal over a point may actually have a group action on it. And this is how the idea of topos was born. And now we know the birthday. It was Monday, April 21st, 1958. Unless Pierre tells me I'm completely wrong about this. and you're going to have to really argue to convince me. And maybe you won't. I hope you won't. It was born that day. Jean-Pierre Serre gives a talk that day. He's concerned with getting 𝐵 cohomology groups. He and Grothendieck are concerned with it. Lots of people are interested in the project. I don't know how many other people were actively pursuing it, but they're actively pursuing it. And that day, he presents decisive progress on getting the one-dimensional cohomology groups, just the one-dimensional case, by using what he calls unramified covers. Okay. I didn't get a lot of sleep. I have trouble with R's anyway, you know, but he gets the one-dimensional case. Grothendieck comes up right after the talk. Serre has recorded this in a publication that we now have. Grothendieck comes right after the talk and says, that's going to give all of them. That's going to work in every dimension. And Serre, this is also recorded, and I believe him. He says, that was a little hard to believe. Because he says, I knew how hard I worked to get the one-dimensional case, and I just didn't think it could be done in higher dimensions. But Grothendieck had a reason. Grothendieck now knew the 𝐵 étal spaces. Between his Kansas paper and his Tohoku paper, if he knows what the étal spaces are, he knows the cohomology. Any reasonable definition of étal space will give a cohomology, and he knows how to do it. He comes up with axioms for a generalized topology. You're going to have a small category of generators patched together by direct limits and finite inverse limits. This is almost like taking a set of subsets of a topological space. Think of the, and patching them together by unions and intersections. Arbitrary unions and finite intersections. So now it's starting to look like open subsets of a topological space. Compare the idea of a subbase for a topology, where you need those unions, and it's got to be closed under intersections. Oh, a subbase doesn't even have, you're going to need intersections. But also compare the Tohoku axioms, because we were talking about arbitrary colimits. Colimits are like unions. Finite limits, limits are like intersections. So now the Tohoku, it's Tohoku, I'm just not good at pronunciation. Now the Tohoku axioms start to take a more conceptual form. Now they start looking like the standard definition of a topological space in this context. Only we're not going to be talking about unions and intersections of subsets of a point set. We're going to be talking about colimits and limits of some category of generators. It's trivial that if this works at all, the abelian group objects in that category will be an AB5 category. That's just built right in. And he knows that every AB5 category has a canonical cohomology. He's already proved, in the Tohoku paper, he proved this gives a cohomology. And he's sure it will be the correct 𝐵 cohomology. And here again we have Serre's description, I think very apt description. Grothendieck in those days was always optimistic. But it's not a groundless optimism. This is what he's sure of. He said, So what are unramified covers? Well, we've already seen one. If we're covering the circle, unfortunately, I can't draw the difference between a disk and a circle. This is just a circle. It's just a line. And you have this double cover of it. Now, over any point, you get 2 points, and they can be switched by a Galois action. You have a Galois action switching this thing all the way around. So above a point here lies an orbit. This is 𝐶𝐸. This is 𝐶𝐸 talking about topological spaces, in particular about algebraic varieties with a Zariski topology. This is one of the generators. Grothendieck, now the thing is, because it's algebraic geometry, and 𝐶𝐸 wants these to be algebraic varieties mapped onto this, because it's algebraic geometry, these will have to be finitely many layers. Basically, they need to be roots of polynomials. There's only finitely many roots for a polynomial. Grothendieck says, that's what won't give us an AB5 category. We've got to take arbitrary co-unions. We've got to take arbitrary unions of these. We'll get a sheaf category by allowing arbitrarily many of these things. But locally, each part of it will be an unramified cover. And I am convinced, and we'll be happy to talk about this at more length, that Grothendieck gets this picture during 𝐶𝐸's talk, sees that it looks like a subbase for a topology, and says, yeah, we can make this happen. And that's why he goes up and says, this will work in all dimensions. So there we have the birthday. I don't know what time that seminar was. I did verify it's a Monday. I have not checked what the weather was that day, but you can find those things out. Yeah. Yes, 60 years ago last week, this is his 60th birthday. I announced that on Facebook. I couldn't find a more appropriate forum. Now, developments by 3 years later. There is a shortage of published documentation of the next few years. Well, shortage, I guess there's always a shortage depending how much you want. There's less than I would like to see. But by 3 years later, he's realized some things. Étale spaces in topology, it's not true. Oh, and this one has this nice property. Take anything here. Above it, it looks like 2 copies of what was there. But in topology, that's not generally required. In topology, it may be that one of these things goes off to infinity, so that when we look at what's happening over this part, well, that doesn't look like 2 copies of this part. But around any point up here, there's a neighborhood. So it's no longer true that over any small part of the base, it just looks like copies of that thing stacked over each other. It is true that any point in the space over the base has a neighborhood that looks just like the part it lies over. So Grothendieck has said, okay, that's a little different. So we have to, instead of the finite unramified maps that 𝐶𝐸 used, let's use flat unramified maps. And I will thank 𝐶𝐸 also for pointing this out to me. One of the first times I talked to him, we talked about étale maps, and the first thing he wanted to tell me about étale maps was they're like finite étale maps, but they're trivial in the fibers, not in the base. That was, he wanted to get that out, and I think that change was made.
Who said that?
𝐶𝐸 did to me, yeah. Yeah, it was like, say, the first thing he wanted me to know. Also, Grothendieck failed to find what he says a certain number of exactness axioms which imply all the others one would want to deal with. He can't make that axiomatic approach work. And in hindsight, we'll see sort of why. He couldn't get it to work. Well, it's those Giraud properties that he tends to forget. You know, he didn't think of them in the first place. So provisionally, this word provisional is a quote both from the Buffalo Lectures and from 𝐂𝐨𝐳. This is the provisional definition of topos, is the one he comes up with. He says, instead of axiomatizing this category of sheaves, let's construct the sheaves. by saying how many copies of each generator lie in a sheaf and how they're patched together. He said, I'm going to actually construct these étale spaces out of the generators. I would like to have taken coproducts in a category, but you can't take coproducts in a category if you don't know what the category is, right? You can't just say, I want the coproduct of these, if you don't know in what category. And today we know much more about that ambiguity because we've developed topos theory. But Grothendieck at the time just couldn't see how to do it. So he's going to, instead of actually taking colimits, he's going to give a construction. Well, what is that? How many copies of each generator, how they're patched together? Well, that's a presheaf on the category of generators, which was already an available idea in Paris at that time. We're going to define presheaves on the generators, which today we will even say the category of presheaves is the free co-completion of the category of generators. So that's natural. If you want colimits, well, where? Well, how about in the free co-completion? But this is, I say, that's hindsight. That's not Grothendieck at the time. And then, well, okay. Oh, also, tech error command there. And also compare the standard construction of an étale space from a sheaf. You make it as this kind of a union. You say, the sheaf, how many copies of this did the sheaf stack over here? And how did it patch with others? This is how you construct an étale space from a sheaf. Well, it's the same way he constructs these presheaves. And we have to know that if you've got a patching that's compatible over a cover of some open set U, U here is an open subset of the thing we're interested in. It's not just, doesn't necessarily have to be the whole thing. Once you know a compatible patching over a cover has to imply a patching over U, and having said that, you now have 𝐵𝐵𝐻𝐸 de V, which in SGA1 he says visiblement inspiré de Serre. By 3 years after that afternoon, he's invented the 𝐵𝐵𝐻𝐸 de V, visiblement inspiré de Serre. It goes on to develop. By fall of 1961, okay, that was spring of 61 when SGA1 in print edition appeared. By fall of 61, he goes to Harvard. Artin remembers, I asked him to tell me the definition of étale cohomology. He laughed. Okay, this is a quote by Alan Jackson in the notices. Actually, we argued about the definition for the whole fall. He does not yet have a definition of étale cohomology. He's got a motivation. He's got a method. He does not have a definition. Why does he not have a definition? Well, there are technical issues. Should we use all schemes or separated schemes? Should the covers be finitely presented or not have to be finitely presented? Should they be generated by finite covering families? Should we not assume that? Now, it turns out that if you drop any one of these assumptions, all the ones down the line become uninteresting. So we don't have 8 independent possibilities. We have, I think, 6 independent possibilities. But these issues have not been decided by fall of 61. We know this because Artin laughed at the idea, and so we argued about it the whole fall. Artin lays out these alternatives in his mimeographed booklet, Grothendieck Topology 62, which Grothendieck clearly liked because he brings Artin over here for 63, 64 to work in the SGA and to edit SGA4, co-edit. By 1963, Giraud had given his topos axioms, those 4 that, you see, if you're fond of topos theory, you remember them. But at the time, and Grothendieck was already saying he couldn't remember them. As Giraud says, ce résultat et la mise au point de la notion de site qui l'accompagnait ont été incorporés dans théorie des topos et homologie étale des schémas. I said everything in italics was a quote of Grothendieck. Well, this isn't quoting him in context, but he does name the book a lot in the tapes. So it's okay that this is in italics. But what I want to call your attention to is I think Grothendieck looks at it the same way Giraud is looking at here. It's not just an axiomatic result, it's also a mise au point of the notion of site. The notion of site now makes more sense to him because it correlates to these axioms. In Buffalo, Grothendieck repeatedly says you need sites to give proofs. Having repeatedly said that he doesn't think you need to worry about the definition, he does say, well, if you want to give proofs, you're going to need to know the definition. He repeatedly says you need them to give proofs. I will say set theoretically, because this is an issue in my own work, sites in the Źródeł axioms are not as different as you might think. A lot of people naively say, well, the thing is sites are small. The Źródeł axioms deal with large categories. Yeah, but they deal with them in terms of small families. They're really, set theoretically, they're not as different as you might think. For Grothendieck, what they are is they're both slightly technical. Keep saying you need them, but they're not the way to think about the subject. They're slightly technical. Then he comes to morphism of topos. The notion of morphism of a topos into another is quite essential to the notion of a topos, and almost more important than the technical definition, which is slightly involved. So what is a morphism of E into F? Sometimes we may say just a continuous map. In fact, I wouldn't mind saying so, though in the seminar we said rather morphisms. Continuous map is really the intuition. He wants you to think of a topos as a geometric object. Even though this doesn't quite make sense, but there are many mathematical situations which confirm it. We want a definition such that if E is the topos of sheaves on a topological space X associated to a topological space X, and F is a topos associated to a topological space Y, then the continuous maps from E into F, in quotes, I mean the morphisms, the topos morphisms. Notice that's what he's putting in. He's saying in quotes, the continuous maps, in quotes, the topological, the morphism should just correspond to the continuous maps of X into Y, at least if X and Y are sober. There's another issue that I won't go into here, but so they're going to turn out to be what are now called geometric morphisms of the topoi, which I won't give the technical definition, but it does this exactly. For sober topological spaces, the geometric morphisms between their sheaf categories correspond exactly to the continuous functions between them. And there are reasons why it can't be for all topological spaces, but for sober ones it does. So he says, when we speak about a topos, and now, actually, wait a minute, let me refresh my memory on exactly where this happened in the series. Okay, yeah, this is still in the regular series. When we speak about a topos, there are always two intuitions. We think of the topos as something like a generalized topological space embodied through the category of sheaves E. So the intuition here is it's a category of sheaves. He keeps stressing how big these categories of sheaves may be. The motivation is sheaves on a topological space, but a topos is a category of sheaves. But in fact, we think of the topos as being something still different from the category E, the space which is underneath, so to say. The category sheaves on X, topos is a generalization, a topos as category is a generalization of this category. But we think of this category as representing the thing underneath it, the topological space. And we want to think of every topos as being something still different from the category. Think of it as the space which is underneath, so to say. But I have not found a verbal trick to distinguish between a topos and the space we're thinking of. And then there's a long pause. He's thinking. One could just declare that there are such things as topoi, a topos is a generalized topological space where every topos has an associated category, and distinguish between the two. We'll just say, the same as we distinguish a topological space from this category, well, for any topos E, for any category E that has the topos property, we'll distinguish the geometrical, some geometrical object G that it lies over. We'll just say, what do we mean by geometrical objects? They're the things that topoi lie over. But one will never really define what, well, and now he's even saying the topos. Yeah, this is going to be the topos. The topos is that little geometrical object. The category that lies over it is another thing, but one will never really define what the topos is. Never mind. He says this a lot in the lectures. He'll get thinking about something and say, never mind. So we could just say, we know about all these huge categories. And we know that some of them are associated to topological spaces. But we're going to say that all of them are associated to geometrical objects. It's just that most of the time we can't get those. He says the category of sets is pretty huge, but as a topos, it's pretty small because you should think of it as a topological space reduced to one point. The category of all sets is the category of sheaves on a one-point topological space. And a topological space, unlike, say, a scheme, if it's got one point, that's all it's got. It's just a point. So the category of sets is pretty huge, but the topos, the geometrical object, is pretty small. It's just a point. I'm sorry to insist rather heavily on kind of trivial matters, he says. But I think it's very essential to see on one hand these big categories, and on the other hand geometric objects, which are a lot smaller, but these geometrical objects we can't define in any other way. They're just these huge categories. Yeah, he wants a theory of geometrical objects that he doesn't really have. Well, there's nothing surprising in wanting something you don't have yet, right? I mean, he wants new geometrical objects. He says, one could, of course, other times speak almost without any abuse of language, but I think the geometry would get lost. So after a while, when it's comfortable, almost conversely, one reverts back to the geometric language, the language of these small things, and views E as the category of sheaves on the real topos, I mean on the real honest thing, the geometrical object X. The real topos is the topological space, the little thing G that we can't describe, whatever. E, the category of sheaves, that's some big thing that describes this honest geometrical thing. Even if X is a topological space, the usual topological space doesn't exist anymore. The objects of the topos, like sheaves over a space, are spaces in their own right. In fact, they're the induced topoi. That's just how it is, and it just works. That's not a radical statement to say that it works. Yeah, he can't spell it out yet, but it works. It works, and he wants to be able to spell it out. That's why I brought up the thing about categorical logic. He can't make categorical logic into mathematics, and he says he's not even going to try. He's not against somebody doing it. Well, here he wants to do it. He wants to make this mathematics, but he's told us he can't really do it. So I will say, even point set topological spaces are to be replaced by new objects. The topological space doesn't exist anymore. Only the topos, which is now not the category of sheaves that we call the topos. It's the geometrical object underlying it. Missing a verbal trick. These are thoughts of my own. This is not in the Buffalo lectures. And I hope nothing here is italicized. That's not italics, that's math font. Different thing from italics. A Zariski topos, S zar. S is some scheme. What is the Zariski topos of a scheme? Well, it's a space made out of Zariski opens. It's a topological topos. You take the scheme as Zariski topological space. You look at the category of sheaves over on it. Geometrically, it's made of the Zariski open subsets. We don't have time to define that carefully. It's a lattice ordered by inclusion. The subsets, the only relation subsets have to each other is overlapping or inclusion. That's the key point here is that, like any topological space, we're just looking at overlap and inclusion of the opens. And the Zariski topos is like that. I would compare a pane of glass. Take a sheet of glass. It has extent. It's extended to a certain amount. You could even cut it in pieces. But there's no inner structure. Glass has no inner structure. You can break it, but there's no structure inside it. Compare the étale topos on that same scheme. It's made of étale opens. What is the point of an étale open? An étale open is kind of apart. It looks kind of like a Zariski open, but it can unfold into Galois extensions. It unfolds into Galois extensions of any degree. And I would invite you to compare a sheet of mica. beautiful sheet of mica. I think of a nice, transparent, big sheet of mica. You can always split it into any number of thinner sheets. The étale topos is like that. Compare Mumford's drawings of arithmetic schemes over spec Z. They come layered. And we want to make that into geometry. A continuous map from the étale topos to the Zariski topos fuses the orbits together. You've got this sheet of mica that you could have split, but instead you melt it into a sheet of glass. And now it won't split anymore. That's what that continuous map does. This doesn't work very well. When I said missing a verbal trick, I'm not supplying the verbal trick. I'm saying this is what we're missing. This doesn't really work very well. I like the image, but it's not going to go very far. If you just take these topoi without structure rings, forget a lot. You do not want to know the topos of sheaves on the Zariski topology of a variety. Not if you don't know the ring of the variety too. But also topology forgets a lot in all analysis in differential geometry. Topology is supposed to forget a lot. That's the value of it. You forget a lot and you still have something left. They say this is really not going to work very well because more interesting than either of these toposes just by themselves is the ringed topos where you do remember the structure ring. And that's what we don't have a good language for. Now, there are two directions to go with this, two directions that are currently being taken on this. One is general topos theory, the way Joyal, Tierney, and Moerdijk have done it, extending generalized topology. You've got these ideas of locale, étendue. You've got factorization theorems in topos theory that compare to factorizations in topology, generalize them very substantially. You've got properties that make no sense in point set topology, but do here. But this geometrical kind of theory has been developed considerably. I do think that the distinction between gros and petit topos might be crucial in understanding this. Lavier reports that when he talked with Grothendieck about it, Grothendieck liked his reference to that chocolate metal exercise and agreed that it might be. This is just a might be. I'm just saying it might be. It exists. And the other is geometrizing specific kinds of topoi in more special terms, the way I just did over there with the Zariski and étale topos, except maybe do it better, make it work more than that one does. I think both of these directions are going to happen. People are going to continue pursuing both of these. Just want to mention that they are the two. Back to Buffalo in 1973. Grothendieck tells us, SGA4, he says SGA4 is the first 1.5 volumes of the 2-volume seminar devoted to the theory of topoi and étale cohomology of schemes. In fact, he says the initial aim of the seminars was étale cohomology, but one had to write down prerequisites on sites. Oh, I will say, yeah, I should say in connection with this other thing. No, not that far. This is a way people talk about étale and Zariski sites. A lot of what I'm sort of urging to develop as a geometrical view of topos already exists as a geometrical view of sites, but of course then it's not invariant under forming the topos. So this kind of thing is going on partly at that level. Yeah. But one had to write down prerequisites on sites, and the first write-up was pretty awful, he says. The direction of arrows was never clear, which is true. When you read the IHS mimeographs, it's not really clear which direction the geometric morphisms go. And the geometric meaning was very messed up, so we rewrote the whole series of notes. So half of the seminar on topoi, was done with great care. His recommendation is, yeah, that stuff in SGA4 Volume 1, that was done with great care. Because it was rewritten. It was written twice. Other parts were only written once. Notre principe directeur a été de développer un langage et des notations qui soient ceux qui servent déjà effectivement dans les diverses applications. This is already being used. We're just trying to put it into this, de sorte à ne pas perdre contact avec le contenu géométrique ou topologique des divers foncteurs qu'on est amené à considérer entre sites. Yeah, we've got these ideas that are already working some in some way. SGA4 is an attempt to make them work in general topos theory. Okay, when he says principe directeur, you can see he's saying this is not exactly an achievement. If it was an achievement, he'd just say, read the book, it's there. But this is where they're trying to go with it. Pour ceci, les notions de topo et de morphisme de topo semblent être le fil conducteur indispensable et il convient de leur donner la place centrale à la notion de site devenant une notion technique auxiliaire. He really, okay, this is his argument for why topos should be the key idea, and that the provisional form of site, which you need for proofs, he keeps saying you need it for proofs, but it's auxiliaire. Now we're at hour 13. Yes. Where he had, okay, not where he expected to end the first time. He originally expected to end at hour 10. Then he thought he would end at hour 13. Oop. He now estimates 1 or 2 more meetings of an hour and a half on topoi and sites, and maybe a smaller, more technical group on relations between algebraic structures and topoi. As to topoi, I think more and more, by the way, that in the language of topoi, one should really distinguish between the category and the geometrical object, which one has in mind. I mean, he keeps coming back to this. One has to make this abusive language because otherwise one will always be a little torn. Never mind. Yeah. But I also want to stress about Grothendieck, because I think this is systematically important, he's not recommending abuse of language. He's not saying, oh, let's just abuse language whenever it suits us. He's saying this abuse is really important, and until someone can make it mathematics, we should make the abuse. He says you have to, because otherwise I think the geometric intuition gets lost. For instance, the sum of topoi in the geometric sense corresponds to the product of categories. He likes this example. You know what is if you've got, okay, if you've got a topological space here and some other topological space over there, you know what is their union. It's the two of them. I can't draw them differently because the drawing of the union just looks like the drawing of the two of them. And you know what is a sheaf on them. It's a sheaf on this one together with a sheaf on that one. That is, it's the category of all sheaves is the product of these two categories. You take one from here, one from there to get a sheaf on this union. This union, to get the category of sheaves, take the product of their sheaf categories. This works in general topos theory. In any topos, it makes sense to talk about the sum of two topoi geometrically because you take the product of the sheaf categories. Of course, for a standard topos theorist, the sheaf category is the topos, but now for me, the topos is the geometric object underneath. The arrows are just in the opposite direction. Yeah, that's important. I won't go into that here, but, well, it is unpleasant in some situations to identify a topological space with the category of sheaves on it. The space can be pretty small, and the category of sheaves is a pretty huge thing. Every topos has the category of sheaves on it. This is the geometric intuition that he can't really spell out yet. He's still missing the verbal trick. And then we come to universal algebra. And I'll take 7 minutes to go into this. We won't really be able to do it. About 10 or 15 years ago, so again, this is in 73, he's looking back to 58 or shortly after 58, I thought some about universal algebra in regard to a pretty grim seminar of Chevallier's. Back to that one that was a mess. Chevalier does not like categories up to equivalence, so he did everything up to isomorphism. It became a dreadful mess. You know that in some current versions of category theory, people take it pretty seriously that you should do everything up to equivalence. You should not talk about isomorphism of categories. And Grothendieck is saying, yes, in this context, there's a lot to that. This is one reason to use topos. He says there seems to be a one-to-one correspondence between algebraic structures up to a certain notion of equivalence and topoi up to a certain notion of equivalence. There's a remarkable geometric intuition of topoi, and that's the interest of them. I will say the geometric intuition here, he means cohomology. But I think it's important to understand that when Grothendieck means cohomology, he doesn't mean as opposed to intuitive geometry. For Grothendieck, cohomology expresses intuitive geometry. This is not a choice to be made. This is just a way of doing it. So certain notion of equivalence, this has a name today, Morita equivalence. And this is very much the topic of Olivia Caramello's work. What I have not done is listen carefully enough to this to relate it to modern ideas. He does give a two-categorical theory of universal algebra. Numerous examples, lots of insights, and lots of errors. Over and over again, a session starts out with, well, some of the things I proved last time I think are not right. This is going to be some work to really dig into this and find out even just to find out what's Grothendieck's final version within the lectures, let alone what is the current state. And he does start out by saying to people, I am not up to date on this, I'm not paying attention anymore, so you're going to have to tell me. Well, of course, the people in Buffalo aren't much more up to date on it either in 1973, but a lot of it has been done since. There are numerous references to the blackboard. You're listening to the tapes and you hear click, 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 and then you'll hear, now here, click. If you look at this, click. Very frustrating. I don't doubt that a lot of it could be reconstructed if you listen very minutely, but it's painful. It's painful right now to listen to. He talks about accessible categories, disregarding cardinality conditions. Nobody today works on accessible categories without talking about the cardinality conditions. Grothendieck does disregard them. I expect his disregard is in favor of the loosest of them. I expect that it makes sense to a modern expert, but it's only a special case to a modern expert, but I'm not sure. Because it's so hard to tell what he's saying anyway, because he keeps saying, as we wrote here, click, and you don't know what he wrote there. He talks about a pseudotopos, which is a pretopos, which is a Giraud topos, except for the generating set. That's pretty much a current definition, except that I'm not sure how precisely how he intends it. He talks about hypertopos, a strict topos, a topos with all the exactness properties of sets. What he means by that is that arbitrary products preserve epimorphisms. There is no currently standard meaning to all exactness properties of sets. He has one exactness property in mind, that an arbitrary product of epimorphisms would be an epimorphism. So I think this is basically an ill-defined concept. But he does give pre-sheaf topoi as an example. Okay, in a category of pre-sheaves, yes, limits and colimits are both pointwise, and an arbitrary product of epimorphisms will be an epimorphism. So he's got clear examples. I don't think he has a clear definition. He may just mean a topos where the constant sheaf functor preserves all products. That would be one way to clean up what he says. You'd have to really work through what he's saying to decide if that's an adequate way to clean it up. Oh, I know what I need to get to, though, because you will not want to miss this. He tells us towards the end, there's a little trouble with universes, and don't think it's about universes, I'll get to it. There's a little trouble with universes because one has to add such a strong axiom to set theory. Once one adds this universe axiom, one is in a way happy because one has a lot of leeway to do category theory. For example, Deligne has just proved a beautiful theorem on Weil conjectures, and I guess he's used large cardinals. Grothendieck is in Buffalo. He's been in North America for most of a year now. I don't remember exactly when he arrived. You have to use all these topoi, all this general nonsense, and you have to use universes. Jack Duskin, who made these tapes. Oh, I was to mention Lauver's role in rescuing these tapes, too. These tapes could have been lost, I think is fair to say, and Bill Lauver made sure they weren't lost. Duskin took them, but he didn't listen to them afterwards, which is natural. I mean, of course, he didn't listen to them right after he made them, and later on these other things. Duskin says, but isn't there a relative consistency proof for universes? It's not really a new assumption because it's relatively consistent. And Grothendieck says, no. 10 years ago or so, when I came up with universes, I asked a few logicians, and they seemed convinced that there's no hope of proving relative consistency. Now, this sets an interesting limit on Grothendieck's knowledge of logic. A point that I keep making to logicians, Grothendieck cared. Grothendieck went and asked logicians about this. Grothendieck cared to develop the whole idea of universe. But Grothendieck does not understand that there's an easy proof that there can't be a relative consistency theorem as long as you think Gödel's second incompleteness theorem is easy. I mean, it's an easy corollary of Gödel's second incompleteness theorem that there can't be a relative consistency proof here. So Grothendieck goes to the experts and appreciates their answer, but he doesn't himself know the reasoning behind that answer, or at least he doesn't recall it here. Often in these tapes, it's not clear what he really doesn't know and what he's just not recalling in a moment. So therefore, Grothendieck says, therefore the question arises, and he and Duskin both laugh. Do Phase conjectures depend on this axiom? Everybody would be convinced, of course, they don't. But Samuel thought about introducing galaxies smaller than universes. One has to be careful with injectives in such homological algebra to see if you can construct them in this new context. His description of Samuel's idea is badly butchered. The idea he describes makes no sense. Because again, Grothendieck, he's not specializing in a set theory, but he cares that somebody should get it right. He does say, it would be nice to have a context where one doesn't add any real axioms to set theory, and yet one can work with categories without too much afterthought and trembling, take each functor category as another category, etc. Of course, we have a context where you can do a tau cohomology without adding any real axioms to set theory by not really using most of the topos theory. You didn't need it, so you don't use it. But he's saying, no, I want a context where you don't need new added axioms, but you can do all the topos theory just the way you would naturally think of it. And Deligne, the second thing Deligne said to me when he met me was, you know, I think topos is one of Grothendieck's great ideas. Well, he knew that I was coming from topos theory, and Deligne is a very nice guy, and he wanted me to feel like he wasn't, you know, and I don't feel like he's against topos. But Grothendieck is,
What did you say, Deligne?
When?
You said, Deligne said what?
Deligne, when I first met him, it was at the IAS in Princeton, and he comes out and he says hello, and basically the first thing he says after hello is, you know, I think Grothendieck's idea of topos is one of his great ideas, which he substantially says in what is it, quelques idées maîtresses dans l'œuvre d'Alexandre Grothendieck. No, but what and that's what he says to me, you don't need them, you can get rid of them in favor of small sites, but they're a good way to think. Yeah. So, and that's what Grothendieck is. Grothendieck, of course, by the time SGA4 came out, he knew you didn't need universes for the core theorems, but you did need universes to state the theorems the way he states them. And he's saying it would be really nice if we had, and okay, an advertisement for my work, I can now provide this context. I can provide a context radically weaker than even Zermelo's set theory, in which you can do all of SGA4 with no afterthought and trembling, and all the functor categories are categories. It's not really very hard in hindsight. Basically, what it comes to is SGA4 does not use the axiom scheme of replacement. And because it doesn't use replacement, you don't really need that much strength. But of course, at the time they were writing it, they didn't know what they would need because they didn't know what theorems they'd be proving. Now that you know what theorems they proved, you can provide this context. But he does, and he says, I think there's mathematics behind all of this because you have to be careful. It's not good enough to say, I'm pretty sure you don't need set theory. You have to check that you don't need that set theory. And if you want to take each functor category as another category, that checking is not super hard, but it's not trivial. And it wasn't done yet at this time. Somebody who I don't recognize says it feels like some infinite cardinals in models of ZF don't really exist. These infinite cardinals, they're talking in fact about the Whitehead conjecture. No one in the room understands clearly that they're talking about the Whitehead conjecture, and so I won't explain what it is, but you can tell that's what they're talking about. It feels like some of these infinite cardinals don't really exist. Grothendieck says, no, they don't. They exist in the same way as chess playing. They construct powers. You look around in nature, you won't discover any of these things. And then he starts musing. That's kind of nice that 𝐵's conjectures are true. I just got a letter from 𝐂𝐨𝐬𝐧 saying Deligne was explaining the proof in Cambridge at a seminar in honor of Hodge, one of the most beautiful theorems ever proved. I'm thinking it's quite clear he will have used a tau cohomology. He doesn't yet know how the proof has gone. I'm thinking it's quite clear he will have used a tau cohomology. And a tau cohomology, after all, means we've added all the theorems of topoi. Now, Deligne already knows you don't really need all those theorems of topoi. But Grothendieck is saying, well, that's how it's done, is by these theorems of topoi. And Deligne, I mean, when you read SGA 4.5, Deligne thinks about the topos. He just knows you don't formally need it. One has the feeling that there's some hard core, you see. A tau cohomology is computed, and there are very precise things about it. That's the hard core. All these categories, universes, et cetera, are just some kind of fussing around to make the parcel, you see, more appetizing. Really not sure of that word fussing. These are old tapes, and some of them are. I guess you can do mathematics without axiomatizing almost at all. Right? Every time you want a certain theorem, you just do your proof of it over again. You don't need the theorem, just give the proof every time you wanted the result. And so you won't need axioms. So one doesn't really feel that universes are essential. Even the geometry of 𝐵's conjectures can be formulated without reference to any specific homology theory. Well, of course, 𝐵's formulation was without reference to any specific homology theory. The core, the positivity of certain traces, can be expressed in terms of intersection multiplicities. I quote this for the interest of anybody who cares to pursue it. I do not know the proof well enough to know what he means by saying the positivity of certain traces is the core. So somebody could work on that if they wanted to. There is a lot more about this in the tapes, hard to transcribe because he's hesitating, he's restarting, people are speaking over him because they're pretty excited by this point. The problem with this approach is, once you know the theorem is true, you know you could check everything this way. But until you know the theorem is true, you don't know that that check will always work. You have to be able to prove the check will always work for it to count as a proof. And can be done, but you have to do it. I'm not sure one can completely write the conjectures down as a mere statement about algebraic cycles, except by making it even stronger than it is. There's a stronger version that's just about algebraic cycles, but I'm not sure, he says, I'm not sure you can do it except by making it stronger than it is. 𝐂𝐨𝐬𝐧 tells me the most essential use was made of SGA 7. I would be kind of curious to know what the ideas are, because I had no impression it was close at hand at all. This is July 13th, 1973. He's gotten this letter, but he's saying, I had no impression it was close, and I'm suspecting that's because of the standard conjectures. A proof by the standard conjectures was not close at hand at all, then or now. But that's my conjecture. This is what he says. There's much more discussion, including talk about motives that I did not try to transcribe. They joke around a while, then they go to dinner. 2 days before, in the algebraic group lectures, an audience member had asked him, what kind of subjects are you working on now? Grothendieck is startled. What? What kind of subject? No subjects. I've been thinking a little during these last weeks about topoi and universal algebra because this was connected to the things in the talks, but I'm not going to go on. And I won't go into these other topics unless they come up. Hey. Oh yeah, I will. This is from 𝐵. L'ensemble des deux séminaires consécutifs, SGR 4 et SGR 5, qui pour moi sont comme un seul séminaire, développe à partir du néant à la fois le puissant instrument de synthèse et de découverte que représente le langage des topos et l'utilise parfaitement au point d'une efficacité parfaite qu'est la cosmologie étale. Cet ensemble représente la contribution la plus profonde et la plus novatrice que j'ai apportée en mathématiques au niveau d'un travail entièrement mené à terme. This is why you should learn the language of topos. He compares it at one point to building houses. I build houses ready to live in. What I say to mathematicians, a lot of mathematicians will say it's all foundations. I don't care about foundations. But I think Grothendieck is onto something here. Does anybody worry about the foundations of this building? Well, not me or you. But of course people worry about the foundations of the building. The building wouldn't work if somebody hadn't worried about the foundations. And that's Grothendieck's attitude here. This is, you don't need, he's clear, he wants you to not need the SGA to use these ideas. He wants the SGA to be so perfect that you can just use their results without knowing them. But he wants the SGA to have proved it from the ground up. So, is it? Yeah, that's the time you wanted. Okay. Okay, thank you.